Hey everyone, Mr. Skelton here. We are back at it. Unit 6, Lesson 2, and today we're going to be focusing on the opposite of what we did yesterday. Yesterday we talked about exponential growth, so today we're going to talk about exponential decay, something that's depreciating exponentially. All right? And so you're going to see a lot of similarities from yesterday's assignment in terms of the type of problems we do, but in all these situations, our value is going to be decreasing. So let's just jump right into it here with the first slide. It says, suppose you learned 100 new things on a given day, and that each day that goes by you forget half of it. How many of those 100 things will you remember in 7 days? So let's kind of talk about it, and then we'll kind of develop the equation in a similar fashion to what we did yesterday. So we have 100 new things, all right? So let's say on the day 0, we have 100 new things that we have learned. And then after 1 day, that's going to be cut in half. So how did we get that? We took 100 and we times it by a half, and that gave us 50, right? After day 2, that's going to give us 25 things. And so we took 100 times half twice, right? And we played this game before where we go down, and now we're going to go all the way down to day 7. And so that would be, if we're holding on to our pattern here, we took 100 things, we cut that in half, that 100 in half, 7 times. And so if we just take our calculator out here, we're going to go 100. Actually, I'm going to do a little bit differently. I'll go 0.5 raised to the 7th power, and then I'll times that by 100 because we have to follow order of operations. And that gives us basically 0.78125. So we didn't even remember one thing. We got we're close to 75% of one thing remembered after 7 days. Now, the point of this, which is again carrying over from yesterday, is this function notation, which is y equals a times b to the x. Remember that your a value is what you start with. Your b value, in this case, is what we would call our decay factor, or what our initial starting point is getting decreased by, and in this case it's decreasing by a half, so we times it by 1/2, and then obviously our exponent is how many times that decay factor is being generated. Okay, let's go on to problem number 2. So this one says, what will a car be worth? Obviously cars are the worst investment of all time, because as soon as you buy a new car or even a used car and you drive it off the lot, it's already beginning to depreciate or decay in value, right? And all you do is constantly pump money into them anyways: new tires, oil changes, broken parts, shocks and struts, etc., etc. You'll learn that as you get into purchasing cars. So suppose you bought a brand new Chevy Vega in 1977 for $3,400. If the car depreciates in value by 20% each year, what is it worth today? Now, this can sometimes cause some issues because of this percent here, and I'm going to talk about how we need to write that. So if we go to our function notation, which is y equals a times b to the x, what is our initial value? Our initial value in 1977 was $3,400. Now, here's the tricky part. What are we plugging in for b? Well, here's what you have to think. A lot of people are going to put 0.20 here. That is not the case. Remember, if I times this by 1, which is 100%, or a 1 as 100% would be just $3,400. What is the car? Here's how I always think of it. The number that goes in here when you're talking percentages is what is it worth, right? So if it's depreciating by 20%, it's worth 80%, or 0.80, and that's what needs to go in there for x, okay? And so what is it worth today? Well, it's 2018, so let's just do some basic math. I think that's 41 years, right? From 1977 to 2018, so we're going to go y equals 3,400 times 0.80, because the car's value is 80%. It's depreciating 20%, but it's worth 80% each year, and we want to calculate that over 41 years. I'm going to put 17, so 41 years. So we'll take our calculator, we'll go 0.8, we'll raise that to the 41st power, and then we'll times that by 3,400, and we get 0.3615. We'll just go 0.36. So it's basically worth 36 cents, which is not what we want there. But hey, it's worth something, right? All right, moving on. Let's go to this next question. This is a tough one here. This is called the white whale population question, and it says suppose the white whale population in 2001 was at 120,000 whales, and by 2006 the population was 112,000 whales. Can you write an exponential decay model that uses to predict the population? So what I'm asking you to do is come up with this equation on your own, and then use that equation to make a prediction for the year 2016. Okay? This question should probably get updated. It should probably be in 18, and we can do that. So how do we do that? Well, if you remember from our first lesson notes, we were able to generate this equation from 2 points, right? An x and a y and an x and a y, and we were able to plug those things in here. So this is what we're going to do. I'm going to basically say 1 comma 120,000. Now the way I'm getting that point 1, basically I'm saying years after 2000. Okay, I'll just make the math a little bit easier for you to do. So 1, because it's 2001, 1 year after 2000. Then my second point is going to be 6, because that's 6 years after 2000, so 6, and then 112,000. And so there's my point. And if you remember from yesterday, we want to take the larger x value, xy, xy, and we're going to plug both of these points into our function and generate a value. So we got 112,000 equals a times b. Our x value is 6. Remember, we're going to divide. Remember yesterday when we were dividing these two? So you get 120,000 a, b to the first. So when you take your calculator out, let's see, 112,000 divided by 120,000 gives me 0.9 repeating, and I'm going to keep that in my calculator so I can get an exact answer here. My a's are going to reduce down to 1, and I get b to the 5th. So I need to take the 5th root, essentially. If I'm going to 5th root both sides, I need to take the 5th root of 0.93 repeating. So in my calculator, I'm just going to go take that answer, so I'm going to raise it to the 1/5 power. Remember, taking the 5th root is the same thing as raising it to the 1/5 power. And I get so my b value is 0.9862. And I'll just go to 4 decimal places. I won't write the whole thing, but I'll try to keep it as close as I can. So then I want to generate an a value. If you remember from yesterday, we would just plug this into either one of the 2 equations. So I'll plug it into this bottom one here. So basically I have 120,000 equals a times, my b value is this to the 1st power, so it's just essentially 0.9862. So I'm going to take 120,000, and you can keep the exact answer because you can do it like this. If you keep this loaded in your calculator to 120,000 divided by second answer, and now you get your a value of 121,667, and we'll just have the since we're talking about whales here, we won't make a decimal point because we don't want to have a decimal whale. We'll just have a whole whale here, so we'll round down. So it's basically 121,667. So once we have our a and our b value here, we can write the equation, because that's what this asks us to do. Y equals 121,667 times 0.9862 to the x power. That is the function that models the situation. And it says, can you make a prediction? Let's go 2018, since that's the current year we're in. So all we would do, because years are, x is basically representing years after 2000, so we would plug an 18 in right here. So we'd go 0.9862. We'll raise that to the 18th power, hit equals, and we'll times that by 121,667. And that gives me a total of 94742. And so in 2018, there should be 94,742 whales. Right? So we got to do our part to take care of the whale population, and that's how you do that problem. All right. Last slide is just, we're going to kind of compare and contrast growth and decay here. This is a good slide for you when you're getting ready for a quiz or a test, just to hone in on some of the central themes from exponential growth and decay over the past 2 lessons. So what's the difference, right? Well, we know that they share the same equation. They both have y equals a to the bx. The biggest difference is with growth, your B value is always going to be greater than 1, right? If you remember some of the problems that we did from lesson 1, if this was a 2, that means your initial amount is doubling, right? If I had like y equals 3 times 2 to the x, we kind of did this in class, I believe. Or basically like, okay, I'm starting with $3 and it's going to double. It's going to double every day. That's because my B value, which is right here, is bigger than 1. With decay, your B value is always going to be less than 1. So if you're doing a decay problem, it's always less than 1, just like what we did today on the slides. So that's important to know. Graphically, what is the difference in the graphs? Well, with growth, our graphs, we're going to keep it in the first quadrant, so there's your x, there's your y. When you graph things, it has a starting point, and then it exponentially grows. As x increases, your y values are increasing, okay? And that's what it's going to look like. With decay, when you go to graph this, again, you'll have a starting point, but then it's going to decay. Now, one thing we didn't talk about is why this graph never crosses the x-axis. And so I want to do that now with you real quick. If we go back to our car problem, which was a little far-fetched, right? We ended up getting 36 cents. Will this value of 36 cents ever drop into the negatives? No, it's not. Because basically, remember, we're taking 80% of the value. It's decreasing by 20%. So if this keeps decreasing by 20% each year, it's never going to get negative. In fact, you'll never get to 0. You're basically, if you take our 0.36, right? Try to get this on the screen, and we times that by 0.80, we get this. And if you I'm going to times that by 0.80 again. And then you look at, I'm timesing by 0.80. We've done this where we just keep hitting enter, 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 enter. So I'm taking 80%, 80%, 80%, or I'm essentially. I'm never getting to 0. I'm getting really, really small numbers, but I'm never going to get to 0. It's like taking half of a penny, right? If you take half of a penny and keep taking half and half and half and half, you're never going to get to 0. It's impossible. So that's why when you graph these things, they're never going to cross over into the negatives. The only time that can happen is if you were to have a situation where your graph started negative, right, and then exponentially grew. That's where, you know, it's a little bit different, but we're just talking about some of the basics here. Last thing, how do you use the annual percent of increase or decrease to find the growth factor? So this is kind of what we were doing with the car situation, right? So if you had a 20% increase, if something was increasing 20%, so let's say you have Google stock and it's increasing 20% every year, what does that look like? Let's say you invested $100, right? What are you timesing that by, that $100 by each year to generate the value of your stock? You're timesing it by 1.20, right? Because remember, if something's growing, it has to be larger than 1. It's increasing by 20%. So remember, the 1 represents 100% of the value of our $100 plus the 20% that it's growing, right? Take 100, times it by 1.20, and after 1 year, we would obviously have $120. That just makes sense. What if it's a 20% decrease, though? Let's say your Google stock, right? You have $100. What goes in here? What's your B value? What are you timesing 100 by if you're decreasing by 20%? Well, remember, it's what is your stock worth? We talked about this. What is it worth? That's what you want to put in here when we're talking about decrease. It's worth 80%, which should make sense. Take a look. 100 times 0.80, that would be $80. After 1 year, you'd have $80. That would make sense. That's a 20% decrease in your stock. Okay? So real important that you understand when we're talking about percents, whether increase or decrease, what your B value is. That's important. What is the B value? And make sure you know what you're putting in there. Okay? I'm sure you'll still have some questions, and that's totally normal. I look forward to tying up any loose ends with you in class. reteaching any of these slides if you want to do that. We just have to make sure that we're communicating with each other, and be love to help you out any way that I can so that you feel comfortable with exponential growth and decay. All right? We'll see you soon.